And in this lecture, I am going to derive the complex flow potential, complex uh, complex flow potential of a doublet scalar flow potential string function stream lines and stream lines all for a doublet. Mm. So the doublet in fluid mechanics means actually it is a pair of source and sink. So a doublet consists of a source and sink. It's a source at some point and there's a sink. And for this derivation of this doublet, we will have the midpoint of the centers of the source. This is a source, center of a source. This is the center of a sink. And the midpoint of the source and sink is coinciding with the origin of the coordinate system xy, Cartesian coordinate system. So, so there is a source and there is a sink. Both have the same strength, n, and let the distance of separation of the centers of source and sink be 2a, so that this distance is a and this distance is also a. So, so the semi distance or half the distance between the centers of source and sink is a. So we call this doublet. The doublet in fluid mechanics is defined as a pair of source and sink placed along a line in such a way that the strength of the source and sink both equal, and it tends to very large value. The source tends to, the strength tends to a very large value, and the distance of separation or 2a, or thereby a tends to 0. So m tends to infinity and a tends to 0. And in that case, if you take limit a tends to 0, m tends to infinity, m into a is equal to limit a tends to 0, 1 by m tends to 0, a by 1 by m. This will have a 0 by 0 form, and thereby this will have a finite limit lambda. So the limit m a tending to 0, m tending to infinity, ma is a finite value lambda. Then we call this as a doublet. So the distance of separation is reduced to very small value and strength is increased to very high value. So this also a flow singularity, and such a flow singularity is called a doublet. Now our first aim is to find out the complex flow potential for a doublet. So we have a source, so for which the complex flow potential we know it is m by 2 pi, and the source is placed at point minus a 0. So that is the center. Center of the source is at minus a. So it will be logarithm natural is at minus a. So it becomes m by 2 pi logarithm z plus a, and this is for the source. So let me mark it as f1. Similarly, for the sink we have minus m by 2 pi logarithm of z and this one is placed at a0. So we will have this z minus a minus m by 2 pi log z minus a, and by the principle of or by the method of superposition we can write fz of the so-called source sink pair as f1 z plus f2 z, that become m by 2 pi is common logarithm of z plus a minus logarithm of z minus a, which will become m by 2 pi logarithm of z plus a by z minus a divided by z minus a, and this will write it as 2 pi logarithm of 1 plus a by z divided by 1 minus a by z by dividing z from numerator and denominator. Now we have a simplification for this. This is equal to m by 2 pi logarithm of 1 plus a by z into 1 minus a by z raised to minus 1. So that is m by 2 pi logarithm of 1 plus a by z into, this is of the form 1 minus x the whole raised to minus 1, which is 1 plus x plus x squared plus x cubed plus etc. In this, we will apply one limit of that, saying stating that the limit that a tending to 0. When a tends to 0, we can assume a squared and all. So this the square terms will be a is tending to very small, so a squared will be tending to very small, and we neglect. So we can write as m by 2 pi logarithm of, this is 1 plus a by z will, is there, this 1 plus a by z will remain almost equal to 1 by 1 plus a by z, or 1 plus a by z the whole square. So that becomes m by 2 pi 2 times the logarithm natural 1 plus a by z. So this cancels. So we have this is equal to m by pi logarithm of 1 plus a by z. Now we know the expansion of logarithm of 1 plus x, right? Logarithm of 1 plus x we can substitute here. So what is the logarithm of 1 plus x? Those who remember, they know that x minus x squared by 2 plus s cubed by 3 minus x raised to 4 by 4 plus etc. Those who don't know, we can obtain this logarithm of, and plus this expansion you can easily obtain if you write logarithm of 1 plus x is equal to integral of 1 by 1 plus x dx equal to integral 1 plus x the whole raised to minus 1 dx, which is equal to integral. This is 1 plus x the whole raised to minus 1 is 1 minus x plus x squared minus s cubed plus x raised to 4 minus etc. The whole integral dx, which is x minus x squared by 2 plus x cubed by 3 minus x raised to 4 by 4 plus etc. Plus there will be a constant of integration. And if you substitute x is equal to 1, x is equal to 1, if you substitute, we will have 0. Logarithm 1 plus 0 is log 1 is 0. So this is 0, this is 0, this is 0. So 0 minus 0 plus 0 minus 0 plus etc. plus c. That gives you c is equal to 0. So this c goes. So we have this. So we will write that m by pi logarithm of 1 plus a by z is x a by z minus a squared by 2z squared plus a cubed by 3z cubed minus a raised to 4 by 4 z raised to 4 plus etc. So we do one thing. In this, we will have this 1 by pi, and we take this m inside so that we can apply the limit m in the a. M in the a by z. So here also m in the a by 2z squared into there is an a plus m in the a squared by 3z cubed minus etc. And you know that 1 by pi, sorry, that's a mistake from here onwards. So this expansion is log is not repeated. So this expansion of log, really here there is a log 1 plus a by z. This symbol is not there. This log symbol is not there. So we have ma is equal to lambda by z minus, right, 1 by pi into, this is lambda by 2z squared, and a tending to 0 becomes, so like that, 1 by 3z cube, and this a squared is put into 0, tending to 0 becomes 0. So that way it will reduce to lambda by pi z. Lambda is a constant, pi is a constant. We replace lambda by pi by mu by z. So this is the complex law potential for a doublet of a doublet. So we can write it once again. Fz is equal to by z, where mu is a constant called the strength of the doublet. So this is the equation for the complex law potential of a doublet. So by having found the complex law potential of Fz is equal to mu by z, we can find the isopotential, sorry, the scalar flow potential and the stream function. So phi plus this phi plus I z. So what you have to do is you have to take this into real and imaginary part. For that, the complex that polar coordinate system is good. So mu by, right, z is equal to r e raised to I theta. So which is equal to mu by r e raised to minus I theta, that is cos theta minus I sin theta. So that will give the real part phi and the imaginary part psi. So phi is equal to mu by r cos theta, and psi is equal to minus mu by r sin theta. So this phi is now written as a function of r and theta in the polar coordinate system. Similarly, psi is also in r and theta. We can write in Cartesian coordinate system also. So we can write phi of xy, that is mu by r, and cos theta, you know, x is equal to r cos theta. So therefore cos theta is equal to x by r, and this is r into r, this is r squared. So r squared in Cartesian coordinate system is x squared plus y squared. Similarly, psi of xy we can write as minus mu y by x squared plus y squared. Fourth, in polar coordinate system, this is Cartesian coordinate system. So now, what is isopotential line? Isopotential line is the curve of a constant value of phi. Constant phi. Say phi 1. So mu by r cos theta is a sorry, I will write it Cartesian coordinate. Mu x by x squared plus y squared is equal to phi 1. So this implies x squared plus y squared minus mu by phi 1 x is equal to 0. So this is a circle. This is a circle. It's a circle. So this is a circle with the center on the x-axis. So the radius of the circle is mu by 2 phi 1. So radius of the circle is this, and this is a circle touching the y-axis. So it is like this. So the center, and the radius is mu by 2 phi 1. So this is an isopotential line. With the phi is equal to phi 1. So similar lines you can draw for different values of phi. Similar, all that will be circle. All that will be having the same structure, so it will be circle touching the y-axis. So it will be like that. So there is another circle which is touching y-axis like that. So maybe for higher values of phi, higher values phi increase of phi will cause the radius to reduce. So you will have another circle. Another circle like this. So it will be center will be coming closer and closer like that. It will continue. So you will have circles like that. Okay. So this is about the isopotential line corresponding to different values of it will be all circles. So one more circle is one more term will be something like this. So like that, if you for actually we can have the circles on this side also. Circles on this side you will get for negative values of Suppose you are having a negative values of phi, then you will have circles on the left hand side. Like this, like this. So that is different values of phi. So it will be there. Okay, this is actually a circle. Okay, all are circles. Okay. Similarly, if you look at the stream function, constant value curves of stream function are called streamlines. So we can draw a streamline for a particular value of stream function. So we have minus mu y by x squared plus y squared is the equation for psi, and that we are writing it as some psi 1, positive psi 1. For positive psi 1, you will have the equation x squared is x squared plus y squared plus mu by psi 1 y equal to 0. So this is a circle. Again, this is a circle with the center on the y-axis. The radius of the circle is mu by 2 psi 1. So like this, there will be circles which is these circles will be touching the x-axis. These circles will be touching the x-axis. So you will have circles like this. So these okay, these center is for this one is mu by 2. Center will be at mu by, that is negative 0, x is 0, y is minus mu by 2 psi 1. So it will be like that. And for negative values of the stream function, you will have negative values of the stream function. You will have circles on the top like this. Okay. There's some problem with the drafting. Okay, so the isopotential lines and stream lines will be like this. So this is about the doublet, and we will see what happens, what kind of flow situation arises when a doublet. This is actually a doublet. When a doublet faces a uniform stream of flow, then what is the equivalency of that? We'll see in the next